Hey guys, so yesterday you learned about arithmetic sequences and series, and so today we're going to learn about geometric sequences and series. So the only difference is instead of having a common difference where you're adding the same number each time, in geometric sequences you have a common ratio where you're multiplying by the same number each time. So like in this first example right here, you go from 1 to 3, and to get there, you're multiplying by 3. From 3 to 9, you're multiplying by 3, and so on. So that number that you're multiplying by is going to be called your common ratio. So the recursive formula, which you should pause and write down, is basically saying that the current term or the term you're looking for is going to be equal to the previous term times that common ratio. So pause here and get all of this down and then move on to the next part. So this is just asking like which of these are geometric sequences, and if it is, find the common ratio. So what I want you to do is pause it and look through and see if you can figure out which one are geometric sequences, and then unpause and we'll go through them together. So the first one, to get from 3 to 6, you're multiplying by 2. To get from 6 to 9, you are not multiplying by 2, you're just adding 3. So on that one, it looks like you're adding 3 each time, so that is an arithmetic sequence, so that is a no. It is not a geometric sequence. The next one, to get from 2 to 4, you're multiplying by 2. 4 to 8, you're multiplying by 2. 8 to 16, you're multiplying by 2, and so on. So this one is a yes, and the ratio, the common ratio, is going to be 2. The next one, to get from 1 to -1, you're multiplying by -1. From -1 to 1, you're multiplying by -1. From 1 to -1, you're multiplying by -1. So as long as that pattern continues, this one is a yes, and the common ratio is -1. The next one, to get from 4 to 2, you are technically dividing by 2, but that's the same as multiplying by 1/2. From 2 to 1, you're multiplying by 1/2. From 1 to 1/2, you're multiplying by 1/2, and so on. So that's a yes, and the ratio is 1/2. And on E, from 2 to 4, you're multiplying by 2. From 4 to 16, you are not multiplying by 2. And it looks like in this one, each of these is being squared. So that is not going to be considered a geometric sequence. So for the formulas, we already talked about the recursive formula, and then there's also going to be this explicit formula. So the explicit formula is going to be a sub n, which is the term that you're looking for, is going to equal the first term times the ratio, the common ratio, raised to the n minus 1 power. So for the n minus 1 power, if you're looking for, say, the 17th term, then whenever you're raising it to the n minus 1 power, you would want to raise it to the 16th power. So it's just whatever term you're looking for, it's that minus 1. So go ahead and pause and write this formula down as well. So then we're finding the common ratio and writing the explicit formula in these, and we're going to use that to find the 11th and 15th term in these. And if you have that formula written down, then that's fine. You can use that. That is not something that you're going to have to memorize, so keep that in mind as we're going through here. So first I'm going to find the common ratio. So to get from 1 to 3, I am multiplying by 3. From 3 to 9, you're multiplying by 3, and so on from 9 to 27. So my common ratio is going to be 3. So then I want to write my explicit formula. So that's a sub n, and it's going to equal the first term, which is 1, times the common ratio, which is 3, raised to the n minus 1 power. And so then to find the 11th term, we're going to actually use that. So I would have a sub 11 equals 1 times 3 to the 11 minus 1 power. So then that's going to end up equaling, the 1 is going to cancel out. It's not going to affect anything. So it's 3 to the 11 minus 1. So that would just be 3 to the 10th power, which is going to equal 59,049. So why don't you guys pause here and try to do the second example on your own. So on the second example, starting with finding the common ratio. To get from 3 to 1, you're dividing by 3, which is the same as multiplying by 1/3. From 1 to 1/3, you're multiplying by 1/3, and so on. So the common ratio is just going to be 1/3. And so then for the explicit formula, we're going to have a sub n equals the first term, which is 3, times the common ratio, which is 1/3, raised to the n minus 1 power. So now we're going to use that formula to find the 15th term. So a sub 15 equals 3 times 1/3 to the 15 minus 1 power. So that is going to end up being 3 times 1/3 to the 14th power. And I can go ahead and tell right now that 1/3 to the 14th power is going to work out to be like a really, really small number. But let's go ahead and type it into the calculator anyway. So I had 3 times 1/3 to the 14th power. And yeah, you get something that's like in scientific notation whenever you do that. So let's just see if it'll change it to a fraction for us. I'm not sure if it does. No, that's not even going to change it to a fraction for us. So it's just going to be like a really, really small number in this case. So the e to the negative 7th is the same as saying like 6.27 times 10 to the negative 7th. So that's just written in like scientific notation. So that was 6.27 times 10 to the negative 7th. So that's just a really small number, and that happens sometimes in these because they grow so fast, or in this case, they're getting like so much smaller so fast. So that is going to be the answer to that one. So then we're moving on to series. That was some sequences, and now we're moving on to series. So this is to find the sum of a finite geometric series. And again, you don't have to memorize this formula because I know that this one looks a little bit intimidating. But if you're trying to find the sum of the first n terms, then what you're going to do is you have the formula S sub n, so that's just saying the sum of that many terms, is going to equal the first term times 1 minus the common ratio to the n power, which is just the number of the terms that you're trying to add up, divided by 1 minus that common ratio. So go ahead and pause here so that you can get that formula down. Okay, so then in these, it's telling us to find the sum, and then this is written in sigma notation. So it's a little bit different than if you're just given the numbers in a sequence. So I'm going to start off by noting the fact that in sigma notation, whatever the number is inside the parentheses, that's going to be your common ratio because that's the number that you're multiplying by each time. So then as you're trying to find the sum, you need the first term is one of the things that you have to start with. So to find that first term, you're going to have to actually use the n equals 1 because that's where you start. And so you're going to plug in a 1 for n. So it'd be like 4 times 0.3 to the first power. And that's going to give you your first term. So I'm going to come to my calculator and I would have 4 times 0.3 and then it's just raised to the first power and you get 1.2. And so then moving forward from there, whenever you're trying to find the sum, you would have S sub n equals your first term which we just found was 1.2, times 1 minus your common ratio, which is 0.3, raised to the n power. And so the number of terms that we're adding up is 12, so that's going to be to the 12th power, divided by 1 minus just the common ratio, so 0.3. And so then you're going to type all of that into your calculator, and that will give you the sum. Okay, so I typed all of that in, and I got this 1.714 number, so I'm just going to round that to 1.71. And that would be the sum of the first 12 terms of that sequence. So then again, I want you guys to try pausing it here and trying this example on your own, and then unpause when you're ready to see me go over it. So in this example, you're trying to find the sum of the first 5 terms. So again, we want to find that a sub 1, or that first term first. So a sub 1 is going to equal 3 times 2 to the first power. And so that's just going to be 3 times 2, which is going to be 6. So then moving forward from there, we would have the sum of n terms, or in this case, we're doing the sum of 5 terms. So you could do the sum of the first 5 terms. So you could put a 5 right there, equals the first term, which is 6, times 1 minus my ratio of 2 to the nth power, and we're finding the first 5 terms, so to the 5th power, divided by 1 minus 2. And then you would type all of that in and use that to find your answer. And so when you get all of that typed in, it comes out to be 186 is the sum of the first 5 terms. And so that is going to be your answer for that one. Then moving forward, there is a such thing as an infinite geometric series. So that means that it's not going to end after the first 12 or the first 5 terms. We're going to add up all of the terms up to infinity in that entire series. So for that to converge, which means for that to equal a number in the end, that common ratio, or the absolute value of that common ratio, has to be less than 1. So it can be negative, but if it's negative, it still needs to be between -1 and 0. It has to be less than 1, or the absolute value has to be less than 1. So if an infinite geometric series converges, then the sum is written with this formula. S equals the first term divided by 1 minus the common ratio. And that's it. That's the whole formula for that. So you have to determine if it converges first, and then after you determine if it converges, the formula ends up being a little bit easier than when you're finding the sum for finite geometric series. So on this slide, we're just looking at which of the following of these series will converge if we're adding up an infinite number of terms. So to find that, you're going to be looking at the common ratio of each of these and use that to determine if it converges or not. So remember that that common ratio, it's going to have to be, the absolute value of it has to be less than 1. So in other words, it has to be in between -1 and 1 for the series to converge. So go ahead and pause it here and try to find the common ratio for each of these, and then decide if the series converges based on that. Okay, so on this first example, to get from 8 to 4, you would be multiplying by 1/2. To get from 4 to 2, you'd be multiplying by 1/2, and so on. So on that first one, my common ratio is 1/2. And so since 1/2 is less than 1, that means that yes, this one does converge. So then on my next one, to get from 1 to 1.5, you'd multiply by 1.5. from 1.5 to 2.25, you'd be multiplying by 1.5 again. So that means my common ratio is going to be 1.5. So no, it does not converge because that is greater than 1. On C, to get from -2 to +4, you'd have to multiply by -2. From 4 to -8, you'd have to multiply by -2, and so on. So my ratio is -2. The absolute value of -2 is +2, which is greater than 1. So this one is also not going to converge. And on my last one, from 243 to 81, you'd be multiplying by 1/3. From 81 to 27, you'd be multiplying by 1/3, and so on. So my ratio on that one is going to be 1/3. And so then that's less than 1, so that does converge. But I also want to mention on this, C was the only one that we did that had a negative with the common ratio. A negative common ratio can still converge. It just has to be between -1 and 1. So I don't want you to think that just because it's negative, it's not going to converge, because it is possible if it was like -1/2 or -1/4 or so on. So that still can converge even if it's negative. So then these are the two examples from the previous slide that did converge. So on the first one, from 8 to 4 to 2 to 1 and so on, we had that our ratio was 1/2. So we want to find the sum of all of the numbers in that entire series. So we're going to have S equals the first term, which is 8, divided by 1 minus the common ratio, which is 1/2. And so then you would just type that into your calculator. So I'm going to get my fraction bar in there, and I had 8 divided by 1 minus 1/2. I'm just going to put 0.5, and you would get 16. So that would be the sum of all of the numbers in that infinite geometric series. It's going to converge to 16. So then why don't you guys try the next example? So pause and then unpause when you're ready to see it worked out. So on this one, the ratio was 1/3. And so for my sum, you would use the first term, which is 243, divided by 1 minus 1/3. And so that is going to equal, and again, I want to get my fraction in there, that's going to equal 243 divided by 1 minus 1/3. And that's going to be 364.5. And so that is how you find the sum of an infinite geometric series. So then I want to do an example of this in sigma notation. So notice when it's in sigma notation and it's an infinite geometric series, it has infinity on the top, meaning that you're adding up all of the numbers from 1 to infinity. So again, the ratio is going to be that number that's inside the parentheses. And then to find a sub 1, you can plug in whatever number is down here in for n. So for this one, a sub 1 would be 4 times 0.6 to the 1 minus 1 power. So then that's going to be 4 times 0.6 to the 0 power. Anything to the 0 power is going to be 1. So that's just 4 times 1, which is going to be 4. So this number in front, in that case, is the first term. So if you ever see them where they're set up like this, where you have the n equals 1 on the bottom, and then your exponent is n minus 1, then you can assume that the number in front is going to be the first term. So then to find the sum, I would have s equals my first term, which we said was 4, divided by 1 minus 0.6 for my rate. And so then I just want to calculate that. So I would have 4, well, let me get my fraction bar in here to stay consistent. So I would have 4 divided by 1 minus 0.6, which is going to give me 10. So the sum of all of the terms in this series that's represented with in sigma notation right here is going to be 10. So that is about it for geometric sequences in series. So just make sure that you got all of your formulas written down from this video and you should be good to go.